Look up at the night sky, and you are only seeing a fraction of reality. Everything visible on the electromagnetic spectrum, every star, planet, and galaxy, accounts for 5% of the universe. 27% is composed of a substance that emits no light and blocks no radiation, dark matter. We know this vast amount of invisible material exists because of its unmistakable gravitational footprint. It exerts a massive pull on the visible objects we can see, dictating the movement of entire galaxies. That undeniable physical influence launched an 80-year scientific hunt. Astronomers have been chasing a cosmic ghost, a substance that shapes the universe, even though it remains impossible to touch. The search began in the 1930s. Swiss-American astronomer Fritz Zwicky was observing the Coma cluster, a massive grouping of thousands of galaxies bound by gravity. Zwicky measured the speed of these galaxies and found a discrepancy. They were moving far too fast. Based on the mass of the visible stars and gas alone, the cluster lacked the gravity to hold itself together. The galaxies should have been flying apart into deep space. To explain why they stayed clustered, Zwicky theorized that an unseen mass was providing extra gravitational reinforcement. He called it Dunkel materia, or dark matter. In the 1970s, astronomer Vera Rubin shifted the focus from clusters to individual spiral galaxies, measuring the orbital speeds of stars at their outermost edges. Standard physics suggests that stars on the far rim of a galaxy should orbit much slower than the stars near the dense core. Rubin found that these outer stars were spinning at the exact same speed as the stars in the center. At those speeds, the visible mass of the galaxy was insufficient to keep the outer stars attached. Without a massive halo of invisible matter completely enveloping the spiral, the galaxy would tear itself apart. The convergence of these two findings confirmed that an unseen physical presence was overriding our observations of gravity across the entire cosmos. When astrophysicists call this material dark, they mean it is literally invisible. It does not emit, absorb, or reflect any form of light on the electromagnetic spectrum. It passes through regular matter without a trace, potentially flowing through the Earth and our bodies right now, interacting with the universe exclusively through its mass. Because of that immense mass, we can map dark matter using gravitational lensing. A massive dark clump warps space itself. When light from a distant galaxy travels through that warped space, it curves around the invisible mass, distorting the image we see on Earth. By measuring those distortions, scientists can reverse engineer the precise location and weight of the dark matter causing the warp. We have proven the substance is there, but particle physics still struggles to define what it actually is. The most prominent candidate is the WIMP, or weakly interacting massive particle. These are theorized to be heavy, slow-moving particles forged in the heat of the Big Bang. A competing theory points to axions, hypothetical subatomic particles that are extremely light and carry very low energy. There is also the possibility of primordial black holes, microscopic or supermassive objects formed during the first chaotic fraction of a second of the universe. While long considered cold and sluggish, new research suggests dark matter could have been born blazing hot, moving near the speed of light before eventually cooling down to help form galaxies. Physicists currently have no confirmation of which theory is correct. It may be a combination of these candidates, or something entirely beyond our current laws of physics. In January 2026, the James Webb Space Telescope provided the most detailed look at this mystery to date. Using its MIRI instrument, Webb analyzed a region of 800,000 galaxies in the constellation Sextans to produce a high-resolution map of the area's dark matter. The data revealed a sprawling cosmic web where invisible dark matter and regular matter perfectly overlap. This alignment identifies dark matter as the structural foundation of division of the universe, acting as the scaffolding that determines where every galaxy and cluster must reside. In the early universe, this invisible scaffolding was responsible for pulling primordial gas and dust together at its densest intersections. Dark matter clumped together first, providing a gravitational head start that allowed the first stars to ignite far earlier than they could have on their own. This early ignition was critical for our own existence. Those first stars acted as chemical factories, fusing simple hydrogen into the heavy elements like carbon, iron, and oxygen that were later ejected into space. Without dark matter forcing this process to start early, The universe would not have had enough time to enrich itself with the specific elements required for rocky planets like Earth to form. We are the direct products of this unseen structural influence, yet we have still never detected a single particle of it. We're closer to answers, but dark matter remains the universe's greatest unsolved mystery. Every star and galaxy we can see is anchored to a hidden architecture. This invisible scaffolding dictates the large-scale structure of the universe, acting as the gravitational glue for everything in existence. In 2026, the James Webb Space Telescope produced the highest-resolution map of this material to date. By measuring how gravity warps the background of deep space, Webb revealed the exact distribution of this unseen web with twice the sharpness of previous observatories. The mystery began in the 1930s with Fritz Zwicky. While studying the Coma cluster, Zwicky calculated that the visible galaxies lacked the mass necessary to stay bound together. Without some form of dark matter providing extra gravity, the entire cluster would have drifted apart eons ago. Decades later, Vera Rubin confirmed the problem within individual galaxies. She observed stars at the extreme edges of Andromeda orbiting impossibly fast. According to the Nuller laws of physics, these stars should have slowed down as they moved away from the center, yet they moved as if pulled by a massive, invisible halo. In the Bullet cluster mid-collision, pink regions show ordinary gas crashing and slowing due to friction. The blue regions, the majority of the mass, continued forward, unimpeded. This separation proves dark matter doesn't experience drag. It interacts almost exclusively through gravity. We have undeniable proof that this material belds and binds the cosmos. We see its footprint across millions of light years, yet we remain blind to its physical identity. Identifying this substance is difficult because it defies the standard rules of observation. It does not emit, reflect, or absorb light, and it allows electromagnetic radiation to pass through without a trace. This lack of interaction makes dark matter harmless. It passes through lead, concrete, and our own bodies as if we were made of empty space. Without direct visual evidence, physicists must deduce a profile for dark matter by precisely measuring the gravitational distortions it leaves on the cosmic background. This investigation carries significant stakes for understanding reality. If we fail to find a physical particle, it suggests that our current laws of gravity, the very equations Einstein used to describe the universe, are incomplete and require a total correction. The leading candidate for decades was the WIMP, the weakly interacting massive particle. It was a mathematically perfect solution that emerged naturally from the theory of supersymmetry. To find them, scientists built massive detectors in deep underground mines, shielded from the noise of the surface. Despite years of operation, these sensors have yet to record a single confirmed collision with a dark matter particle. The lack of results has shifted focus to the axion. Originally proposed in the 1970s to solve a flaw in nuclear physics, the axion is theorized to be trillions of times lighter than an electron. Instead of heavy individual particles, axions would behave like an ultra-low energy field permeating the universe. This changes the strategy of the hunt, requiring researchers to look for subtle field fluctuations rather than direct impacts. Scientists at CERN and labs across Germany are deploying high-intensity magnets to coax these theoretical axion fields into a measurable form. Both candidates rely on sophisticated mathematics, but the continued failure to detect either one in the real world is forcing astrophysics to broaden the search. In July 2026, researchers published a new model suggesting that dark matter is a complex syndicate of different particles rather than a single species. This two-component theory proposes that different types of dark matter particles occasionally collide and interact with one another rather than passing through everything in total silence. Internal collisions cause mass segregation. Heavy particles sink to the galactic center, while lighter ones drift outward, forming the low-density halos of dwarf galaxies. Meanwhile, the dense central pool of heavy particles creates strong gravitational lensing, magnifying light from distant galaxies. This model unifies these two contradictory observations, diffuse dwarf galaxies and dense central clumps, into a single consistent mechanical process. Recognizing dark matter as a dynamic, evolving ecosystem means we need to adjust our detection methods to account for a moving target. To capture this ecosystem, scientists are turning to indirect detection, searching for the high-energy radiation released when dark matter particles collide and destroy each other. This is similar to a medical PET scan, which maps internal tissues by detecting the gamma rays produced when antimatter and matter annihilate inside the body. The Fermi telescope has already identified a mysterious gamma-ray glow at the heart of our galaxy, which could be the first evidence of these collisions in action. Verifying this requires a new generation of tools. The Vera C. Rubin Observatory and the Nancy Grace Roman Telescope are preparing to map dark matter distributions at 4,400 times the scale of current surveys. NASA's 2027 COSI mission will join this effort, specifically hunting for the positron signals that would confirm the existence of a multi-component dark matter syndicate. These observatories are waiting to witness the precise, high-energy flashes that occur when these invisible masses finally interact. With high-resolution maps, more complex theories, and advanced space telescopes, the investigation has reached a critical stage. The next decade will reveal if these tools can finally identify the particles that shape our universe, or if their silence confirms that the answer lies in a fundamental correction to our laws of gravity.